Okay, so this is 2013 free response number 6 on magnetic fields. So what I'm going to do, I need room to solve this. So here's the given question, but I'm going to erase the text. So you should have this problem in front of you as we go through it. So, but hey, actually, before I erase this, I want to mention something. Notice what they say here. So the mass per length of wire. So right here. How do we deal with this? You know what we're going to say? We're going to say, all right, the length of the wire is going to be what? 1 meter. If we make the length 1 meter, then what's the mass going to be? 5.6 times 10 to the negative 3 kilograms, right? That's how. So we're going to say, all right, these wires, let's just make the length 1 meter. And you get the exact same answer, like as you go through the calculations, you'll get the exact same answer if you would have chosen 2 meters. Because if you chose 2 meters, the length would be double, but then so would the mass, right? So the easiest thing to do is just make it 1 meter long. And that's what we're going to assume in this problem. All right, so let's make some room, clear this out. Okay, so here are our 2 wires. The first thing they want us to do, is they want us to calculate the magnitude of the magnetic field produced by wire X at the position of wire Y. So it's like you could just take wire Y and eliminate it. Just take it out completely. All we're doing is we're finding the magnetic field from wire X at a point down here. Okay? So the equation that does this, the equation is magnetic field at a distance from a wire is mu naught I over 2 pi r. Mu naught is a constant, which you don't have to memorize. It'll be given. 1.26 times 10 to the negative 6 Tesla meter amp over amp. The current would be the current producing the magnetic field, which here is 65 amps. That's the current in wire X. And then 2 pi r is how far you are from the wire, which is 0.025 meters. So you punch this in and you get 5.21 times 10 to the negative 4. Tesla. Magnetic field is in Tesla. All right, pretty easy. Okay, part B. Calculate the magnitude of the current in wire Y. Okay, so to do this, you have to read part of what's stated in the problem. In the problem, what they told us was that wire Y is free to move. You know, it's free to move up and it's free to move down, but it's floating there, right? How do they word this? In the problem, it says wire Y, which is part of a second circuit, is free to move vertically and is suspended at rest by the magnetic force. Okay? So dude, looking at wire Y, if wire Y is suspended there, there has to be 2 forces canceling, right? So what's one force on wire Y? One of the forces on wire Y is going to be what? mg down, right? The wire has a mass, so we got mg down. Now, if wire Y is suspended, there has to be a vertical force up that cancels mg. What is this vertical force up that's canceling mg? It's the force of the magnetic field, right? Now look, the way to think about this problem. In this problem, think about wire X. Wire X is the source of the B field, the magnetic field, okay? And then wire Y is going to get a force. It gets a force from the B field. Oops, I can't write. The B field produced by wire X, right? That's how you're going to think about this problem. Wire X produces the magnetic field. wire Y is sitting in that magnetic field. So by the way, guys, which way is the magnetic field from wire X going down here? Underneath wire X, which way is the magnetic field going? You have to use right-hand rule number 2. So take your thumb, point it in the direction of the current. So underneath wire X, down here, the magnetic field's going in, and then up here, it's coming out, right? So I'm going to drop these X's even farther down, right, like this. So these X's and dots, this is the magnetic field from wire X. Okay, now, what's the equation for force on a wire in a magnetic field? B, I, L, and I showed you guys in lecture. Where does BIL ultimately come from? It just comes from QVB. Oh, and don't forget sine theta, but what's the theta in this situation? 90, because it's the angle between the current and the B field, which in this case is 90. Okay, so for wire Y to be floating here, these two forces must be canceling. So basically, BIL must be equal to mg. And then now we can solve for I. So I is mg over BL. Okay, so we're assuming the length to be 1 meter, right? So then the mass will be the 5.6 times 10 to the negative 3 kilograms, right? Okay, and then G, just use 10. And then B, we already calculated 5.2 times 10 to the negative 4. Hey man, what if you would have gotten part A wrong? If you got part A wrong, then that means that this would be wrong, which means your answer to this question would be wrong, but could you still get 100%? Yeah, if you show the work. If you show the work, you'll still get 100.
Is it like that on the actual AP?
Oh yeah, the free response is that, you know, you're going to cash in on points because you could still get 100% on this as long as you showed the work. Okay, so so this comes out as about 108 amps, like 107.5. We'll just say 108 amps. Okay, and then the second part, which way is the current in wire Y? It's either going to be to the right or to the left. So to figure out the direction of the current, you have to do right-hand rule number 1, the flat hand rule. So look, the way you do it, the force of the magnetic field on wire Y has to be up. So your palm has to be up. Okay? Which way is the magnetic field going? In. How do I know the magnetic field's going in? Well, remember, wire X is the source of the magnetic field. And then what's the magnetic field from wire X doing down here at wire Y? It's going in. So right-hand rule number 2, your 4 fingers are pointing into the paper. Your palm is facing up. Which way is my thumb? To the right. So the current in wire Y must be to the right. Okay, so this is to the right. Okay, moving on. Part C. Now wire Y is moved to a new position that is closer to wire X. So let me revert this. We'll clean this up. So they're changing things up. Let's still erase this. So they tell us that wire Y, wait, what did they say? Wire Y is moved to a position, no, sorry, part C. Wire Y is moved to a new position that's closer to wire X. So dudes, if we take wire Y, I'm just going to grab wire Y here, and we start moving him closer to wire X, what's going to happen? Look, is mg going to change? Is that going to change mg? No. Will it change the force of the magnetic field? Yeah, because why? What's happening as we get closer to wire X? The magnetic field gets stronger, because remember, wire X is the source. In this problem, wire X is acting as the source of the magnetic field. F equals BIL, so the magnetic field gets bigger. Right? The B is going to get bigger. So therefore the force. So what does that mean? what's going to happen to wire Y? It'll accelerate up, right? So the correct answer for C is wire Y will accelerate up, right? Okay, and then D, suppose that wire Y is moved to a position 0.025 meters above wire X. Okay, so I want to do it. Sorry guys, I got to go through the steps here again. Let's erase the, oops. So we're going to take this. Scoot up here. So we're going to take wire Y, grab him. Wire Y is now going to be boom up here. And let me erase this. Get rid of that. Get rid of that. So this distance is the 0.025. 0.025 meters, like that. Okay, so what are they asking? What change in current, if any, must occur to maintain equilibrium? Okay, so dudes, wire X is still the source. What's the magnetic field from wire X doing up here, above the wire? It's going which way? It's going out. Right? Right-hand rule number 2. So these dots, what do these dots represent? The dots represent the B field from where? Wire X. Okay? So now look, in order, so we got, if we look at wire Y, mg down, so we need the force of the magnetic field to be up still. But now which way must the current be going? So now you got to do right-hand rule number 1. So we need so your 4 fingers are coming out of the paper, your palm is up. Which way is your thumb pointing? To the left. So the answer to this question is the current in wire Y must be reversed. So question D, current in wire Y must be to the left. Or what else could you have said? The current in wire X must be to the left, and the current in wire Y to the right. That would work too.